So there are three things that we are trying to understand. One is whether the neutrino is its own antiparticle, which has to do with the Majorana, and as I mentioned to you, was already okay. So we discussed yesterday the expression for the half-life or inverse half-life for neutrinos double beta decay, and as I mentioned, is a product of phase space factor, nuclear matrix elements, and the mass squared of the neutrino, where the average mass is the mass of the three species of neutrinos mediated with the matrix element that couple those species to the electron neutrino. And from oscillation experiments, we have some information about the masses and about the three different species. And I showed yesterday a graph where if I plot here the square of the mass, we can have two situations. One in which we have two light neutrinos and then a little bit heavier neutrino. So this is, let's call nu1, nu2, and nu3. And from oscillation experiments, we have measured the differences in masses here and here. But we have not measured the absolute scale of the mass, which is what we want to understand. What is the absolute scale of the mass? And I mentioned yesterday that we have two possibilities, one called the normal hierarchy, in which we have two light and one little bit heavier, or we can have the opposite situation in which we have one light and two heavy, and so this is usually called the inverted. And so the idea is now to see whether with this experiment we can measure the absolute scale of the masses of the neutrino. So this is one of the most fundamental problems in neutrino physics, understanding what are the masses and understanding whether it is a Majorana particle or not, which is particularly important for these lectures since these are the Majorana lectures. In recent years, there has been, this question has become again of much interest in view of the fact that neutrino the physics has many anomalies, the reactor anomaly, all sorts of anomalies that are present, and so people have suggested the occurrence of other neutrinos, which are called sterile neutrinos, and there are suggestions for a fourth neutrino, a fifth neutrino, and sixth neutrino, and you can make it because there are so many different papers and different suggestions for these neutrinos. Each one of them is designed to solve one of the anomalies. One of the most popular one for these anomalies is a fourth neutrino with a mass of about 1 electron volt and very weakly coupled to the others. I will discuss later on calculations for the effect of the presence of this additional fourth neutrino on double beta decay. What is the effect of adding this additional neutrino? So
these are light sterile.
These are light. These are light.
What is the official position on the right-handed neutrinos? What is most likely to happen there?
I will try to discuss that there. And also there is the question of not this light neutrino, but also heavy neutrinos. And there is an entire range. And so what we actually have done is to study the process as a function of the mass of this neutrino. So you can put it there. And also the question whether they are just left and right or whatever it is. Yesterday I showed a little bit of that, but I'm going to show it again and put that here. Good. So this is the program. And so now, if you want to extract a neutrino mass, you have to calculate these two as accurately as possible. And this depends on nuclear physics. This depends on atomic physics. Why? Because the two electrons have to come out from the inside the nucleus, to go through the cloud, and these electrons are relativistic in some cases. So we have to do a very accurate atomic physics calculation for this. And so the plan is today I'm going to discuss the calculation of the nuclear matrix element. Tomorrow I'm going to discuss the atomic physics calculation, and then I'm going to put everything together to see what are the current limits on neutrino masses that we have at the present time, and discuss some of the experiments. Very good. So the lecture today is going to be related to nuclear physics. It's going to be a little bit technical, at least the first part, so I apologize for that. But unfortunately, these calculations are very complicated, and therefore it's good that at least we discuss in part what it is. So maybe we can close this. So today there is going to be a discussion on the evaluation of the nuclear matrix elements for this process. The process is again indicated there. Is a nucleus X decays a nucleus Y by emitting either two electrons or two positrons, but no neutrinos. And here is an example, the decay of germanium-76 to selenium-76 by emitting two electrons. And repeat, the half-life for the process can be written in the following fashion. The inverse half-life is the phase space factor, the nuclear matrix elements, and then here is whatever physics is beyond the standard model, including, for example, if we have some right-handed currents or other things, and which will depend on the masses of the neutrinos, the couplings of the neutrinos with the electron neutrinos, and so on. And for the case of light neutrinos, this is just the mass of the neutrino squared. And three processes that have been discussed extensively in the literature are exchange of a light neutrino. Light means much lighter than 1 MeV. Heavy neutrino much larger than GeVs. And also the possibility of the emission of a massless scalar boson called Majoron here. And this process can occur because at this the vertex an antineutrino is emitted, but if the antineutrino is equal to the neutrino, then can be reabsorbed at the other vertex and then emitting the electrons and so on. In the recent years, there has been also a fourth scenario with the possibility of emitting a sterile neutrino or antineutrino and then absorbing by the other one. Now, in this case, it is not possible to separate the nuclear matrix elements from the physics beyond the standard model, and everything is entangled. And so this complication here is somewhat more complicated than the one that was in the previous slides. Now, coming specifically to the nuclear matrix elements, here is the expression of the nuclear matrix elements, the operator M, which is written in the following way. I put in front the axial vector coupling constant GA for a reason which will become apparently towards the end of this lecture. So I put it in front, and then there is a contribution of gamma octella, then there is the contribution of the Fermi, which I put here as the Fermi coupling constant, the vector coupling constant over the axial vector coupling constant squared. This is because I put in front the GA squared, and then there is the tensor component which is induced from other terms there in the current in the hadronic current will induce a term like a Majorana term. So these two terms are the usual one, Fermi and Camortella, that are included also in single beta decay. This is an additional term which appears here. Now, several methods have been used to evaluate the matrix element. We have to evaluate the matrix element of this operator between the initial and the final states. And some of these methods are indicated here. They have an acronym here. One is called the QRPA, another one is the shell model. Then there is the interactive boson model, which is the model that we have used. And then there is density functional theory and several other models. Now, in all of this model, to evaluate the matrix elements, we have to write them in a form that is relatively easier to evaluate. And so all of them can be calculated using a very compact expression in which there is here the isospin operators changing a neutron into a proton or vice versa. Then there is here a part which depends on the spins of the two nucleons which take part in this process, and lambda equal to 0 and S1 and S2 equal to 0 means Fermi matrix elements. S1 is equal to 1 means gamma of Teller. This is axial vectors, they are sigma essentially operators. And then lambda equal to 2 is tensor. Then there is a radial part, and then there is an angular part. This can be rewritten in second quantized form in this fashion here. And then you see that essentially what this operator does, it annihilates a pair of neutrons with angular momentum capital J and creates a pair of protons with angular momentum capital J. This is because in the process there are two neutrons that are transformed into two protons, or vice versa for beta minus or beta plus. Angela, this is a particular operator that needs to be computed. This is explicit form for the operator to be computed. Okay. Then in this method of interactive boson model, one then maps pairs of fermions into bosons. It's called bosonization procedure. Starting from a pair of fermions, we map them into a boson. The bosons are called S and D because of angular momentum 0 and 2. And then the fermionic operator is mapped into a bosonic operator which has this particular form. And then the coefficients in this expansion are obtained with a particular procedure, which I'm not going to discuss in detail. One is called OAI mapping, was introduced by us already many years ago. And then basis is constructed with this pair of operators, and then one constructed basis and evaluates its matrix elements. Here gives details of how actually the calculation is done, and also the fact that in this mapping of fermion operators into boson operators, one can have either the leading order term or may introduce higher order terms next to leading order or next to next leading order, and so on and so forth. But it turns out by explicit calculations that these next order operators give a small effect, and therefore I'm going to neglect it from this moment on. So, of course, then the matrix elements had to be evaluated with realistic wave functions and of the final and initial nuclei, and these wave functions must be such that they fit the excitation energies, electromagnetic transition rates, quadrupole moments, magnetic moments, so on and so forth. And here is an example of how good are the calculations within the framework of this model by comparing the experimental structure of this nucleus neodymium 150 with the theoretical structure that is calculated here. And as you can see, these are quite accurate descriptions of the spectra of those nuclei. Now this is for light neutrino. Also for heavy neutrino can be evaluated, and here is a list of calculations that have been done, starting essentially in 2008. There are many calculations that have been done, starting in 2008 and then going to 2009, 10 until now. Many calculations are still being done. And here are the results, which for the experimental point of view are the important one. So here 3 models are compared: the interacting boson model, IBM2, the QRPA, and the shell model. And as you can see, there is quite a variation with the mass number. This is a function of neutron number. But the striking feature of this figure is while these 2 calculations are in relative agreement with each other, the calculation with the shell model is very different. It's a factor of 2 different. And this has caused a tremendous amount of discussion, let's say, in the literature to try to understand why there is the difference in this calculation. And this is very important from the experimental point of view, because the half-life depends on the matrix elements squared, and so a factor of 2 means a factor of 4 in the half-life.
Which interaction they use in shell model? That's the problem. Because in the other case it's more effective, they are effective theories.
All of these are effective.
Yeah, but shell model, if you use a realistic interaction, interaction, then
they use a realistic one.
That's not a guarantee that they get.
Of course. But even more so is the model space, or model space in use.
It's it will get the space too. That's
So that's the problem. And so this is an aspect. Here is a result for heavy neutrino exchange, and again you see a factor of 2 difference between different models. But all models make assumptions, as we have just said, and therefore it's important to study the dependence of the assumption made in different models, and this has been done because of the interest of the experimentalists. So there is this is a sensitivity analysis. It's like an experimental analysis for light neutrino exchange within the framework of the interacting boson model. The estimated sensitivity to the input parameters, it may change, the single particle energies, the strength of the interactions, the oscillator, closure energy, and so on. There are sensitivity to model assumptions, and but the bottom line is that if all of these are included, then if they are included in addition, the result is as a sensitivity of between essentially 50%, while if they are included in quadrature is about 20%. So better than this at the moment, as far as the interactive boson model, we cannot do. And the other approaches also, the sensitivity is comparable, although they have not been investigated so much in detail. Similarly, one can do a sensitivity for the exchange of heavy neutrinos, because heavy neutrino exchange is sensitive to short-range correlations, because if the neutrino is heavy, it is the distance that travels between the place where it's emitted and when it is absorbed is very short, and so it's like a contact interaction. So heavy neutrino exchange is very sensitive to short-range correlations, to the fact that the 2 nucleons cannot get close to each other, and so this has to be investigated, and we have done an investigation using different short-range correlations parameterized with Jastrow functions, and some soft and some hard, and so this has been analyzed, and again for heavy neutrino exchange as function of r equal to 0, the Jastrow function expanded into powers of r, as you can see, vanishes if c is equal to 1. So for this type of correlations, since 1 minus c is 0, then if the neutrino is infinitely heavy, the matrix element calculated with this short range correlations vanish. Now, I'm mentioning this not so much because I want you to follow all the details, but just to say that these calculations are very tricky. They're very, very complicated because of the nature of the matrix elements that we need to compute. And therefore, for heavy neutrino exchange, the sensitivity is much larger. There is another source of error, and that is the amount of isospin purity in the wave functions. This error affects both the QRPA and IBM2, not the shell model, because if the calculation is done into a basis which is isospin pure, this does not affect there. But in order to take this into account, because the operator cannot change isospin, neither the Fermi nor the Gamow-Taylor operators can change isospin, because the operator contains T plus, tau plus, which is a generator of the isospin group, and the generator of the group cannot change the value of the isospin or the representation. So updated calculations have been done in 2015. So these are now the final results with all those corrections included. And again, in this result, you see what you saw before, relatively close correspondence between QRPA and IBM2, and the shell model usually lower, although the difference between these two calculations has been reduced considerably. And this is for the heavy neutrino exchange. And so here are the final results for the matrix elements with their error. And this has been done, as you can see, both for light and heavy neutrino exchange in all nuclei that can decay into by double beta decay. INFN is particularly interested into this nucleus, tellurium-130, because the experiment Cuore makes use of tellurium for the study of the neutrinoless double beta decay. You may know that they've completed the assembly of all the detectors, and they will start taking data in 2016. So in a year or so, we will know whether they will see a neutrino mass or not. And also INFN is interested in germanium, because another experiment running at the Gran Sasso is GERDA, which is a collaboration between Germany and Italy, and again is of interest to them. And you see that in effect the matrix element in germanium are larger than the matrix element in tellurium, although by not much. But all the matrix elements are of the same order of magnitude. There is no major difference between one nucleus and the other. So this question that was posed some time ago, which nucleus to use, that's not, from the point of view of the nuclear matrix element, is not particularly relevant as far as this is concerned. Now, another thing that at the Gran Sasso will try is to see whether they can measure the decay to some of the excited states of the daughter nucleus. So this is an idea that was in fact originally initiated at the Gran Sasso, and that is what about measuring the decay to excited states? Now, what happens is that the nuclear matrix elements are comparable order of magnitude. Here is 2.5 and here is 5.4. However, the phase space factor is different, because here the Q value is larger than there. And therefore, yes, may be possible but it's not quite likely. The only good aspect of this is that then instead of measuring the half-life, they can concentrate on another signature of the decay, which will be the de-excitation of the state by gamma emission to this other state. And this usually is much simpler signature because they will have to look for photons with precisely that energy rather than looking for the half-life. So this is again another interesting aspect that will be tried at the with the Cuore experiment for tellurium, matrix element outside the state. Here is a summary of those matrix elements. These matrix elements are smaller than the case to the ground state, except in some cases. Tellurium is a favorable case because the matrix elements are large. Germanium is also a favorable, the matrix elements are large, but all the others are not. Okay, so next we consider the opposite decay, which is the decay by emitting two positrons. So here is an example in which this nucleus cadmium decays to palladium by emitting two positrons. So this process is called 0 nu beta plus, and this or could capture an electron, and so this will be 0 nu beta plus electron capture. These have been calculated, but the matrix elements are of the same order of magnitude as the previous one. So this decay could also be used. Here is the matrix elements, again of the order of the same order of magnitude, about 4. And the final thing that I'm going to mention is this question of the resonant capture. So I mentioned yesterday that double electron capture cannot occur because of conservation of energy momentum. They can only occur if the energy of the initial state is equal or within the width of the energy of the daughter state. And there are a few cases where this occurs. And here is a calculation of those matrix elements for those cases. So the conclusion of this is that all matrix elements of interest to neutrino-less double decay for beta minus, beta plus, beta plus electron capture, and electron captures have now been calculated. And they are all of the same order of magnitude. What?
We can stop here.
We can stop here, yes.
You have a break?
Yes.
5 minutes. 10 minutes. 10 minutes break.
Okay. It's okay. Now the maximum here, the peak, which is in all three calculations, is at about 100 MeV, which is the value of the Fermi momentum of the nucleon in the nucleus, the order of magnitude. So, if Sasha Shavornikov or the others are right that there are neutrinos with a mass of about 100 MeV, wow, we will see them in the experiments. So this is a very important result because, in fact, shows that the nuclear matrix elements are very large in that mass region. You probably know that there are now tests, even at CERN there is an experiment looking for sterile neutrinos, but especially important in fact that the program, the neutrino program of Fermilab is going to be mostly devoted to the search for sterile neutrinos. In particularly for sterile neutrinos with the masses of the order of electron volts, but also masses of order of MeV as well. So this is is an interesting result, as I said, and we will have to wait and see whether sterile neutrinos are there or not, and then to see what is their contribution to double beta decay. In the third lecture tomorrow, I'm going to show explicitly what happens in double beta decay if we add sterile neutrinos. Now, unfortunately, in addition to zero neutrino, we have to study at the same time two neutrinos, because the two neutrino decay happens at the same time as the zero neutrino. This process has been measured in several cases. Two neutrinos have been measured in 10 cases. And we need to do the calculation for comparing with the experiment and for estimating the tail of the two neutrino distribution at the location of the zero neutrino. Unfortunately, the zero neutrino is a small peak. The two neutrino is a distribution because we have the emission of two neutrinos and two electrons. So this is the energy spectra, the sum energy spectra of the two emitted electrons, which has a continuous distribution like in single beta decay. But the zero neutrino is just a line, and here has been multiplied by 10 in order to show a comparison with that. So it's a little bit, what we are looking for is some little bump here, little line at the end of this spectrum. So we need to compute very accurately the spectrum at the location where we expect the zero neutrino. And so that's it.
The curve in between is what?
The curve is the emission of a Majoran. This one is the zero loop with the emission of a scalar particle, massless scalar particle. And also this is multiplied by 10, so even that is small.
That's small. Very small. Not the real problem.
So this calculation is crucial for the experiment, and so we have to do this calculation. So the evaluation is very complicated, even more so, because in this case we cannot use the closure approximation. The momentum of the neutrino that is exchanged between the two is the order of MeV, which is the same order of magnitude of the energy levels of the nucleus. And therefore we cannot do the closure approximation. For zero neutrino, the virtual momentum of the neutrinos is 100 MeV, so the closure approximation for that case is good, but here for the two neutrino is not good. So we need to evaluate the individual matrix elements going from the initial state through the operator sigma tau here to the 1 plus states, and then from that back to the final state with some energy denominator. And so this is a really daunting calculation. And this has been done only in very few cases by various methods, and this is an extremely difficult calculation to do. The separation between phase space factors and nuclear matrix element in this case can be done in two cases, the closure approximation that we mentioned, and also another case in which we consider only one intermediate state, which is called the single state dominance. In that case, this can be calculated by calculating these two-body operators for the decay. But again, I don't want to spend too much time discussing these very detailed calculations. And in the case in which the closure approximation of single state dominance is good, then the calculation for the two neutrino double beta decay can be done in the same way as for zero neutrino, but with a neutrino potential in momentum space, which is of this form, which means that in computation space it's just a constant. So here there are the results for these calculations for the two neutrino double beta decay. Instead, I have to come to another important point, which has been unfortunately missed in the past, and which is going to play a very important role in double beta decay, both with and without neutrinos, which is the quenching of the axial vector coupling constant in nuclei. E qui vengono le dolenti note, because here is where we get into trouble. Now, the previous slides have been obtained by using GA, the value for the decay of the neutron into proton plus electron neutrino and neutrino. The GA is 1.69. But we know from single beta decay or electron capture, and also from two neutrino double beta decay, that GA is renormalized in models of nuclei, is quenched in models of nuclei, and there are two reasons for that. One is that all calculations are done in a limited model space, and two, that non-nucleonic degrees of freedom, delta and star and so on, are not included. This is an old story which was started 50 years ago by Fujita and Ikeda, and then Wilkinson analyzed in the 1970s, and it is a major problem. So what is the origin of quenching of GA in double beta decay? So on the top one, you see a situation in which we have a nucleus N, a neutron little n, and then because of the interactions, then the neutron goes into a delta, and then the delta collects to the W boson and then gives rise to the electron antineutrino, which then, if it is equal to the neutrino, is absorbed by the other here vertex, and so on. So this is one mechanism for quenching the omission of non-nucleonic degrees of freedom. Here I've put in as delta, which is the excited state of the nucleon with mass 1232, but could be some other excited state with the same quantum numbers. So, the quenching factor that one obtains from this is about 0.7. It has been investigated in the past. It is being reinvestigated now. Another origin is this fact that our model space is limited, which means that in effect we are neglecting some excited states of the nucleus, which here is indicated by n excited. And so in this case it's the nucleus that can be going to some excited state and back into the nucleus. This is model dependent because it will depend on the model of the nucleus. This is not model dependent because it does not depend on the property of the nucleon, not of the nucleus. And so this is a model dependent. It turns out that this in heavy nuclei introduces another quenching factor of 0.7, and therefore it looks like the quenching, which is the product of the two, is the order of 0.5. And this is a disaster because this is a factor of 2. But in double beta decay, neutrinoless, there are two vertices, so GA appears to the fourth power, and therefore a factor of 2 to the fourth power is 16. So if this is what is going to happen, the process is never going to be seen, at least for the next 10 years or so. Yes.
The experiment of the Japanese, they claim they say that the quenching is mainly due to the in space and that type of but I don't know if all the experiments confirming or not.
There have been other experiments both effects.
With president general, we say.
But in general,
But this is just because unfortunately this depends on mass number. Okay, I'm going to show you the experiments.
I think that they found a lot of experiments at very high energy, which is restricted to the magnitude
So they're sending to back, but there's also the strain and that resonance region.
But it seems that they were able to explain by this or by this contact, they were saying that now higher condensation is closer.
No, unfortunately it's not. And so let's discuss this a little bit further. So now for each of the various models, one can define an effective axial vector coupling constant by taking the ratio between the calculated matrix element and the experimental one. So here we have a way of trying to extract what is GA effective from the experiment, from the data, both for single beta decay and electron capture, and for some double beta decay with the two neutrinos. And so this is how to obtain from the experiment the GA effective. Now, the values of the nuclear matrix element effective have been obtained experimentally for decay to two neutrinos and two electrons in several cases. And as you can see, this is a summary of all the cases. So these are the data. These are the data going from relatively large values in molybdenum, which was the first case to be observed, to xenon, which is the last case that has been observed in a real tour de force by the experiment EXO collaboration in the United States. The spokesperson of that is Giorgio Gratta, a person that some of you may know because was here in Italy before moving to the United States. And it is the smallest matrix element that has ever been measured for the nuclear matrix element for two neutrinos. So these are data. Now, from this data, by comparing with the various calculations, you can extract the value of GA effective. And now I would like to remind you that the free value for decay of the neutron is 1.269, which is somewhere there. And these are the values that have been extracted from experiment by comparing the results of the experiment with the results of the calculation. And as you can see, although the values fluctuate, in the case of the interacting boson model of IBM2, the values are rather small, about 0.6. You can see here. And we have parameterized them, have been parameterized with the power law, with the power a to the minus 0.18, which with this decrease going from mass 40 to mass 150. Similar story for the interacting for the shell model, in which case for light nuclei, the value that is usually used is for the quenching 0.7, which means that for the GA is about 0.9, but in the heavy nuclei you need a much larger quenching than in the light nuclei. So although the people who do shell model put 2.7 everywhere, this is not appropriate. This is the experiment. So this is a major problem. It's a major problem because now GA effective in IBM2 is about 0.6, 0.5, or GA effective in the shell model is 0.8, 0.7, which means a reduction on the size of the nuclear matrix elements, which means then since they appear squared, there's a reduction there in the inverse half-life, so a longer half-lives. So GA effective has also been extracted recently from single beta decay in QRPA by some people, Suhonen and others, and also Fessler and others have done this extraction with values even smaller than that. And there's not much else to say. Also, there are some attempts, although they're very difficult to do, to extract the value of GA effective from single beta decay into neutrino double beta decay in the interacting boson model, mostly done by Yoshida, a Japanese physicist, and then, but still the extracted values are very small. And recently also Suhonen has done another paper with again another extraction, and all of them seem to be here. And so here are the final result, parameters in some form for the IBM, the QRPA, and the shell model. So all of them show massive quenching of GA. And this is a real problem. Why? Here is why. The impact of the renormalization. The axial vector coupling constant appear to the second power in the nuclear matrix elements because it's there in front. And then when we square it, it's to the fourth power in the half-life. And therefore, all the results of previous slides should be multiplied by factors of 6 to 84 to have realistic estimates of expected half-lives. And this has caused a real problem in the community. And so there is one paper a week on trying to understand this factor. Hamish Robertson, Francesco Vissani, and others, they're all trying to understand this effect. And the question of whether GA is normalized as much into double beta decay is a much debate. Because now we have extracted the normalization for the values of for the experiment in single beta decay and in double beta decay with two neutrinos. So the question is, will the same renormalization occur for zero neutrinos? This is still a point of discussion, because in two neutrino double beta decay, only the 1 plus, the gamma of Teller multiple contributes, essentially. In zero neutrino, all the multiples, 1 plus, 2 minus, etc., 0 plus, 1 minus, contribute. So some of these multiples could be unquenched. We have no experimental evidence, and so we don't know whether this is the case or not. But still, 1 plus dominates. And therefore, my current understanding is GA is normalized in zero neutrinos as much as in two neutrinos. As I said, this is a problem of crucial importance for all the experiments for Gerda, etc. And so it's being at the moment addressed from various sides, experimentally by measuring the matrix element to and from the intermediate of the nucleus in two neutrino double beta decay. Here is an example. There are several other papers doing that. Or another possibility is to theoretically investigate, this has been done by Hakim Schwenk together with others, using effective field theories to estimate the effect of non-nucleonic degree of freedom through the two body currents. So there is a considerable amount of work that right now is going on. Okay. Another question is whether the vector coupling constant is normalized in nuclei. Now, we know that we have conserved vector current hypothesis, and therefore the mechanism 2, which is the omission of non-nucleonic degrees of freedom, will not contribute in this case. However, the mechanism 1, which is the limited model space, could contribute to this, and therefore could be that the ratio GV over GA may remain the same as the non-renormalized ratio 1 to 1.69. Now, no information is available at the moment on the renormalization of GV in heavy nuclei. Eventually could be measured. There is, as you know, a proposal from the laboratory in Catania, Laboratorio del Sud, to measure double charge exchange reactions with heavy ions, which could help understanding this question, especially the relative role of the Fermi versus the gamma of Teller matrix element. But this is still in its infancy, and it's not clear whether the experiment can be done or not be done. And so this is a thing that we have to keep in mind. Perhaps we'll have some result, but it's not clear. Single charge exchange can be done, and has been done extensively, and so we have some information from that. So, coming to the summary of this, to leave some time for discussion, the situation for the nuclear matrix element is that essentially have been calculated in all the processes of relevance to the experiment, both with emission of 2 electrons, 2 positrons, electron capture, double electron capture, and so on, for 0 neutrino and 2 neutrinos. For two neutrinos, they have been measured experimentally, and they've been compared with the calculations. This we are waiting the results of some experiments in the future. So this has been done for light neutrino exchange. It has been done for heavy neutrino exchange. It's been done for sterile neutrino exchange and Majorana emission, and also for the eventual contribution of right-handed currents. And but these are all hypothetical, and the only ones for which we are sure that they exist are the three neutrinos that have been observed now with their with the neutrino oscillations, both atmospheric and reactor and accelerator neutrinos that have been observed. So this we are sure. So the effect should be there at a certain level, but so far it has not been measured. However, as I mentioned in the first lecture, the eventual detection of neutrinoless double beta decay will be crucial in trying to understand the properties of neutrinos, especially whether there are Majorana particles or not, and what is their mass. So for this reason, as you probably know, there are experiments all over the world. There are 2 experiments in Europe, Cuore and Gerda. There are 1 experiment running in the United States, EXO, and 2 planned, one called Majorana, which is quite appropriate with the name of these lectures, and one is called SNOW. One is in Canada, or both of them are in Canada, in the same laboratory where neutrino oscillations, the solar neutrino oscillations were detected, and was the Nobel Prize of this past year to Art McDonald. So there is 2 there, and there is 1 experiment in Japan called CAMLAND, which is going on in Japan right now. And then there are planned experiments in Korea and in China. So at the moment, this is one of the most active areas of research in particle nuclear physics. I do not like to call it particle physics or nuclear physics, in the properties of neutrinos. For this lecture, the idea was to have something related to the experiment here, and so all these materials for all these nuclear matrices are available from writing to Jenny Kotila, who is a postdoc with me, and she will be able to provide in case someone experimentalist needs those matrix elements, needs to obtain those. Now, I still have some other properties here, but perhaps I think since this was heavy in all these nuclear physics calculations, I probably stop here and instead entertain if there are questions that people would like to ask me about both the lecture of yesterday and the lecture of today. Tomorrow we are going to put to the atomic physics part and then put everything together to set some limits on the values of the masses of neutrinos. So tomorrow, in a way, is the clue lectures in the sense that we have the actual limits that at the moment are issues.
I knew that it was no fraction.
Yes.
What can Cameron say about double beta decay?
Oh, they have a program called Kamlan Zen, in which they do the experiment with xenon, and they have a balloon filled with xenon, and so they actually are those who are most advanced, because now, of course, the result, the limit depends on how much mass you have there on the xenon. And so far, the first experiment was with 100 kilograms. Now they are doing 1 ton, so enormous amount of xenon that there is inside there. And they are even entertaining in the new generation to have even more than 1 ton. Mohammed and at the moment they are the most advanced. Unfortunately, Casino is that has the smallest magic segments, so they have not been lucky. Yes.
If you go back one slide,
Yes.
you mentioned. The importance of using a single charge change reaction and double charge change reaction. What is missing in the single charge reaction that we can understand from double charge reaction?
Okay. In the yes. So let me. In the single charge exchange reaction, you can go from this nucleus to the state here. And eventually, if you can do the opposite reaction, you can go from the state to this here. So that's the information that we need from single charge exchange. In double charge exchange, the idea is to go directly from here to here, and so to bypass the middle nucleus, and so to put in the correlations that eventually are in the middle nucleus, to put it into that. However, double charge exchange is a very difficult reaction to do, and especially to do it with heavy ions, because with heavy ions, the energy resolution is not good enough to separate all those things. So it's very difficult. Years ago, there was a possibility to do double charge exchange by doing the reaction by plus by minus on some nuclei. And one could even think, if one would have a sufficient positron beam to do plus and minus double charge exchange. This will be closer to the double beta decay, because this in fact will be essentially doing double beta decay. But it's a difficult experiment because nobody has a positron beam of sufficient intensity to do the experiment. However, I have talked to several people trying to convince them to see whether they could produce a positron beam with sufficient intensity to do this experiment. The idea in Catania is to do it with heavy ions. And so we will see what is the result in that. But most of the information is already in the single charge exchange.
What is this kind of experimental information on the condition of GA?
Okay, for the single charge exchange, you have information on GA by looking at the transition from 0 plus to 1 plus. If you instead go from 0 plus to 0 plus, you have information on GB, because this is the vector part of the current, and this is the capacitor part. So from single charge exchange, you could have information. For the experiment in Catania, the point is that you will be able to measure the double beta decay, the maximum GA squared, the double beta, minus GP squared, the term. This is in neutrinos, apart from the tensor. But in Catania, they will do this with heavy ions. And so they will not be mediated by the weak interaction. They will be mediated by the strong interaction. And so they will get some value of Fa of Campbell plus uncertainty of Fermi. So it would be a different combination of Fermi and Campbell matrix elements. And under perfect kinematic conditions that you can choose, you could select either this or that. So that is the idea behind this experiment.
So this 130 and EU 130.
I believe.
Yes, I agree. But how many cycles they were studying?
In fact, I can probably show you. Maybe I have here. Here is the experiment. And as you can see, they've extracted a myriad of levels.
Yeah, it's very dense.
It's very, very dense.
Yeah, the level density is enormous there.
And here is the calculation that we have done for these things. So, I repeat, it is a very complicated calculation.
Calculation, I understand, but also experiment.
And the experiment so they made calculation. This is the group of Dieter Freckers. And their energy resolutions is kilowatts. Kilowatts.
Probably not the science, but it's one of the
and the experiment are done in Japan, in Osaka, and this is the same group that you were mentioning, who has now extracted all the information. And in principle, they have the information not only on the Campbell matrix element, which was the idea, but also they have information on the Fermi matrix elements because they have some zero plus states, and they have the information on the ion multipoles. Here is the 2 minus state. So in principle, here there are a lot of information.
Behind multiples, it seems to have said here that
so although, yeah, there's not much I can say. It's sort of a dirty physics in the sense. It's not a clean physics like standard symmetries or so on, but it has to be done if we want to understand the experiment.
So maybe we can stop here and continue tomorrow.